What if a 380 kVA diesel generator suddenly posts more than 8 times its normal current? Could your breaker survive it? It's not a tricky question. It's exactly what happens during a short circuit. Today, we are breaking down DC fault current calculation and breaker selection using real numbers, simple logic, and IEEC standards so everyone from students to site engineers can understand it clearly. Let's start with the basics. We have a 380 kVA DC set rating at 415 volt and 3 phase. The first thing we calculate is the rated current, also called full load current. Using the standard formula DC kVA divided by root 3 times voltage, we approximately get about 532 amps. This is the current during normal operation, but faults are never normal. So the question is, how high will the current rise during a short circuit? For that, we use sub-transient reactance, which is written as X double semicolon D. According to IEC 60909, a typical diesel generator has an XD value, which is sub-transient reactance value of 0.12 per unit. This represents the diesel generator's behavior. In the few milliseconds of a fault, the most dangerous moment occurs. Now comes the key calculation. Short circuit current equals rated current divided by XT. So 532 amps divided by 0.12, that is sub-transient reactance, which gives us about 4.43 kiloamps. Now let it sink in. A diesel generator running normally at 532 amps can suddenly deliver up to 4430 amps during a fault. How severe is that fault electricity? We calculate the fault level using root 3 into voltage into fault current. This results in fault level of approximately 3.2 MVA. This tells us how much electrical stress the system must withstand. Now, good engineers never design on the edge. Even though the calculated fault current is 4.43 kVA, we select a conservative design value. So the design short circuit current is taken as 5 kiloamperes. Why? Because of the tolerance, aging, temperature, and future expansion. Now comes the most critical decision. Which breaker should we use? The recommended choice here is an air circuit breaker or a ACB. The breaker rating selected is 800 amperes. Why 800 amperes when the DC current is only 532 amps? Because IC standards required margin for continuous operations, harmonics and load variations. Let's talk about braking capacity. The selected breaker has an ICU of 50 kA as per IEC 60947-2. That means it can safely interrupt up to 50,000 amps, which is far above 5 kA requirement. Even breaker, the ICS is 100% of ICU. This means that the breaker can interrupt fault multiple times without damage. This reliability provides not just protection but stops any mishap. The DC panel itself is designed as per IEC 61439. It's a DC power synchronization panel with IP45 protection according to IEC 60529. So when we put everything together, the DC fault current is calculated using IEC 60909. The breaker is selected using IEC 60947-2 and the panel is designed as per IEC 61439. This is how safe DC system is engineered, not by guesswork but calculation and standards. Thank you.